What you're observing here is a planet orbiting a star with a swarm of 99 smaller objects orbiting the planet in some complicated manner. For the moment, I want you to focus your attention on the single red object in this swarm. I know it's hard to see, but if you look closely, you'll find it. To make it easier to follow, let's trace the path of this object as the planet orbits the star. As you can see, the trajectory of this object is in the shape of a near-perfect square, a situation I find quite extraordinary. How in the world can an orbital trajectory be in the shape of a square? And perhaps more importantly, how was I able to find it? In this video, I'll describe the procedure used to obtain this peculiar trajectory. Greetings, and welcome to All Things Physics, where we zoom in on stimulating questions using the lens of science. In a previous video, we saw that it's possible for a single moon to orbit a star in a surprisingly square trajectory. And today we're going to create a trajectory that's even closer to a square. But before getting started, I want to mention two quick points about the previous video. First, as several viewers noticed, we can produce a number of other interesting orbits simply by changing the moon's orbital frequency and then adjusting its radius, just like we did for the square. Thus, in addition to nearly square orbits, the universe quite likely contains orbits resembling a triangle, a pentagon, a hexagon, and all the other gons you can think of. And second, some viewers were skeptical as to whether such orbits will actually occur when correctly accounting for the interactions between all three objects. Interestingly, at least two viewers carried out their own three-body simulations and showed that such orbits really do occur. Shown here is a three-body simulation of a star-planet-moon system with parameters that closely resemble those found in the previous video. The parameters needed to be tweaked a bit to achieve the orbit shown, but that's not surprising given that we used several approximations in the earlier video. The important point is that the shape of the orbit is extremely similar to what we found previously and appears to be stable for at least a few hundred cycles. With some additional tweaking, I'm pretty confident that a near-perfect match could be found. Let's now turn our attention to today's exploration, in which I'll demonstrate how to create a trajectory that's as close to a square as you could possibly want. In general, when considering a moon's trajectory around a star, four parameters are needed to uniquely specify its path: the orbital direction around the planet, the distance between the moon and the planet, the number of times the moon circles the planet in a year, and the initial angle or phase of the moon. However, as we saw in the previous video, when dealing with a single moon, there were a number of constraints that reduced the complexity of the problem significantly. Ultimately, we found that we only needed to consider the direction and radius of the orbit, which allowed us to use trial and error to search for a square orbit. Unfortunately, as we add additional objects to our system, proceeding by trial and error becomes a hopeless endeavor. So if we're going to have any chance of finding a truly square orbit, we need to be very systematic with our approach. The strategy we will employ is to allow the moon to have a moon, and then allow this new moon to have its own moon, and so on. Moons all the way down, so to speak. One motivation for choosing this approach is because the trajectory of the final moon can then be found using vector addition. We simply need to add a bunch of arrows together, head to tail. As before, we'll assume that each moon travels in a circular orbit about its parent, and that each pair can be treated as its own subsystem. With these assumptions, our system then consists of a series of rotating arrows. The only constraint is that in order to have a closed trajectory, each moon must orbit its parent an integer number of times per year. As shown here, it doesn't take many objects to create a pretty strange-looking trajectory. Our task, then, is to figure out how to adjust the orbital parameters of all the moons so that the trajectory of the final moon traces out a square. To arrive at our destination, we need to take a brief mathematical detour. Consider an arbitrary point in a two-dimensional plane. As you probably know, such a point can be described by its x and y coordinates, and these coordinates turn out to be the components of a vector that points from the origin to the point in question. Such a vector is usually written as the sum of the vector components multiplied by the corresponding unit vectors in the x and y directions, here represented by the symbols x hat and y hat. Another method of describing a vector is by specifying its magnitude and direction using polar coordinates. Here, the magnitude or length of the vector can be found using the Pythagorean theorem, while its direction is specified by the angle it makes with the x-axis. Of course, these two methods for describing vectors are related, and this relationship can be found using trigonometry. Now, there's another equally valid way of describing a two-dimensional vector that involves the use of complex numbers. Recall that a complex number consists of a real part and an imaginary part, represented by x and y respectively. Because a complex number is associated with an ordered pair of real numbers, it's natural to associate a complex number with a point in the xy plane. Thus, if we plot the real part along the x-axis and the imaginary part along the y-axis, then each complex number can be interpreted as a point in what's referred to as the complex plane. But notice that we've already seen that each point in a 2D plane can be thought of as representing a vector pointing from the origin to that point. Therefore, complex numbers can be used to represent two-dimensional vectors, and, as we'll see, this description offers some significant advantages over traditional vector notation. For our purposes, it turns out to be extremely useful to express the complex number using what's called polar form. We do this by writing x and y in terms of polar coordinates and then making use of Euler's formula. In this way, the complex number is written in terms of its distance from the origin, the magnitude of the vector, and its phase, the angle the vector makes with respect to the x-axis. If you're not familiar with Euler's formula, you should be aware that it's a very useful equation in physics. The standard way of deriving this formula is by expanding the exponential function in a Taylor series, and then taking this series to be the definition of the exponential function for a complex argument. We then substitute in the value I theta, expand the powers, and group together the real and imaginary terms. In this form, we find that the real part is none other than the Taylor series for the cosine function, and the imaginary part is the series for the sine function. Knowing that complex numbers can be thought of as vectors and vice versa, it should be clear that adding complex numbers is no different from vector addition. For example, suppose we have two complex numbers given by C1 and C2. We can always find the sum of these numbers by adding their real and imaginary parts. But notice that the vector represented by this sum is precisely what you would get by adding together the two vectors representing C1 and C2. To connect this back to orbiting objects, recall that we are considering a system with multiple moons, and the position of each object is specified with respect to its parent object by a vector. But the math now tells us that each of these vectors can be represented by a complex number. Therefore, the position of the final object, which we will represent with the variable z, can be found mathematically simply by summing together a series of complex numbers. Of course, we know these vectors are all rotating at different rates, and therefore depend on time. So the next thing we need to do is figure out how to describe such rotating vectors mathematically. It turns out that the polar form of complex numbers makes it quite easy to describe rotating vectors, and this is one reason why such numbers are so useful in physics. To proceed, consider a vector of length r and phase theta. If we want the vector to rotate at a constant rate, then the phase must depend linearly on time. Here, theta naught is the initial phase and omega is a constant angular velocity, which can be written in terms of the orbital frequency. This equation shows that the vector begins at t equals 0 with a phase equal to theta naught, and then increases linearly with time, completing f-complete rotations in 1 unit of time. Now, it turns out to be convenient to rewrite our complex number to separate out the time-dependent portion. For simplicity, we'll choose a frequency of 1 cycle per time unit. Our vector can then be written as a constant, which we label as c1, the subscript 1 referring to the frequency of rotation, multiplied by a time-dependent phase factor. The reason for writing it in this form is because the constant c1 represents the initial vector, while the phase factor is responsible for making it rotate. In this particular case, the vector will rotate once per time unit in the counterclockwise direction, but that's only because we chose a frequency of 1. Had we chosen a frequency of, say, -3, then the vector would rotate 3 times per time unit in the clockwise direction. Thus, while the constant out front represents the vector's initial state, the phase factor tells us precisely how the vector will rotate. Now, in theory, a vector can rotate at any frequency. However, each of our rotating vectors are going to represent the position of a moon orbiting its parent. And as we saw in the previous video, in order to form a closed trajectory around the star, the moon must complete an integer number of orbits around its parent each year. The result is that the orbital frequency of each moon is constrained to be an integer. But knowing this, we can construct a system containing an arbitrary number of moons, each with its own radius, initial phase, and orbital frequency, all subject to the closed trajectory constraint. We accomplish this task by adding up the set of complex numbers that represent the positions of the planet and moons, all orbiting at integer frequencies. In the most general case, we would include all frequencies in this sum, with the positive terms representing counterclockwise motion and the negative terms representing clockwise motion. For completeness, we also include a zero frequency term, a constant that represents the position of the star, which we've assumed is stationary. Of course, if the star is placed at the origin, this constant will be 0. The sum we just constructed is known as a complex Fourier series, named after its inventor, Joseph Fourier. Although it might seem mysterious and complicated, remember that all we're doing is adding together a set of vectors that represent the positions of all the objects in our system, with the Fourier coefficients giving the initial state of the vector and the phase factors causing each vector to rotate at a particular frequency. Thus, as long as we know the Fourier coefficients, the trajectory can be found by simply adding the vectors together and setting them in motion. As an example, the nearly square orbit found in the last video was constructed with 2 rotating arrows using parameters we found through trial and error, and therefore represent a Fourier series with only 2 terms. Unfortunately, as we increase the number of objects in the system, the chance of finding a solution by trial and error becomes increasingly difficult. Therefore, we need to find a systematic method for determining the Fourier coefficients. Now, I realize that some viewers may be feeling a bit overwhelmed at this point, so I want to encourage you to hang on just a little longer. Determining the Fourier coefficients is the final piece of the puzzle that allows us to bring everything together. Let's assume someone hands us a complex function that traces out some shape, like a square, as time runs from 0 to 1. We'll discuss where we might get this function a little later, but for now you can just assume it's given. What we're going to do is express this function as a Fourier series, even though we don't know the coefficients, and then use a clever trick to find them. Now, recall that the terms on the right-hand side of this equation represent the positions of the various objects in our system, and after 1 unit of time, everything ends up right back where it started. With this in mind, let's integrate both sides of this equation over 1 unit of time. For those not familiar with integration, it's basically the mathematical process for summing a continuum of numbers. With the exception of the n equals 0 term, every term on the right-hand side of this equation is an integral of a vector that rotates an integer number of cycles in 1 unit of time. For example, the n equals 1 term represents a vector that undergoes 1 complete rotation in 1 unit of time. But notice that this vector points in a specific direction when t equals 0, and then points in exactly the opposite direction when t equals 1/2. So these two vectors will cancel out. And this is true throughout the entire rotation. Each vector has a partner that points in exactly the opposite direction. The end result is that this rotating vector will sum to 0 over 1 time period. In fact, using a similar argument, we can show that every rotating vector on the right-hand side of this equation will integrate to 0. We're thus left with a single term which, being the integral of a constant, is easy to evaluate. When all is said and done, we end up with a formula that tells us how to calculate the coefficient C0. But notice what just happened here. The reason we were able to find a formula for C0 is because the n equals 0 term is the only vector that's not rotating. The trick, then, to finding a formula for some other coefficient is to somehow stop the corresponding vector from rotating. And how do we do that? We multiply the entire equation by an appropriate phase factor. As an example, recall that the n equals 1 term represents a vector that rotates counterclockwise exactly once per unit of time, which means to stop this vector from rotating, we would need to multiply it by a phase factor having the opposite frequency. Thus, we multiply the entire equation by the phase factor with frequency -1. The result is that the rotational frequency of every term gets decreased by 1, making the n equals 1 term independent of time, and causes the n equals 0 term to begin rotating. If we now integrate both sides of the equation, the only term on the right-hand side that's not 0 is the n equals 1 term. So we end up with a formula for the coefficient C1. We can then repeat this process over and over again and ultimately come up with a formula for an arbitrary term in the series. We finally reached the end of our mathematical detour, so let me give an overview of the big picture. We begin with an arbitrary two-dimensional shape, which can be essentially anything you can imagine. We then calculate the Fourier coefficients, which gives us the radius and initial phase of each object in the system. Lastly, all we have to do is add the vectors and start them all spinning, and the final object will trace out the exact shape we started with. It's finally time to put everything we've learned to the test. First, we need to construct a complex function that traces out a square trajectory. Fortunately, because a square is such a simple shape, it's not difficult to parameterize each segment simply by assuming a linear dependence on time. While this isn't the only way to parameterize a square, it's probably the simplest. Second, we need to calculate the Fourier coefficients, and this can be accomplished analytically for a square, though the details are rather tedious. Interestingly, 3 out of 4 terms in the series turn out to be 0, and the ones that are not 0 have a radius that decreases with the square of the frequency. It's convenient to write down the final solution with the terms organized in order of decreasing radius. As should be expected, the first 2 terms are almost exactly what we found for the squarish orbit in the previous video. Armed with this solution, we're now able to simulate the motion of the objects. If we sketch out the trajectory using only 2 objects, we get a shape quite similar to our trial and error solution. But as we add more and more moons to the system, we get better and better approximations to an actual square. And in the limit as the number of moons goes to infinity, the trajectory will converge to a perfect square. It's worth taking a moment to appreciate the subtle beauty of what's going on here. the apparent chaos of the spinning arrows is actually a fine-tuned and highly organized symphony of orbiting moons that has been specifically designed so that the final moon produces the square trajectory shown. I personally find this set of motions to be absolutely mesmerizing. Hopefully, this example demonstrates the incredible power of the Fourier method. It's worth mentioning that, by design, the trajectory shown here has a constant speed. But clearly, such a path will lead to an infinite centripetal acceleration at the sharp corners. In a more realistic trajectory, the object's speed would decrease at the corners, and such a path can be obtained by reparametrizing the curve. Interestingly, although this new trajectory does not look very square-like with only two orbiting objects, it converges to a square much more quickly than the constant speed trajectory. The last thing I want to mention is that the entire procedure discussed in this video assumed that we started with a complex function that traced out a square. Of course, we didn't have to choose a square. In fact, we can choose any shape we'd like, and the procedure is exactly the same. All we have to do is read in a file containing xy coordinates of the points along the trajectory, and then assign them time values. The Fourier coefficients will then need to be calculated numerically, but that's not a problem because there are fast Fourier transform routines, or FFTs, that are designed specifically for this process. Again, once we have the Fourier coefficients, our moons can be set in motion to sketch out essentially any trajectory we can imagine. The first time I saw something like this was in a 3 blue 1 brown YouTube video, and believe it or not, the sight of such an extraordinary animation is what ultimately led me to create my own channel. In fact, the software I used to create the animations in this video was actually developed by Grant Sanderson, the creator of 3 blue 1 brown, and then made freely available to the community. So the animation you see here is my homage to Grant for his generous contributions and for being such a wonderful inspiration. If you're not familiar with 3 blue 1 brown, you really should check it out. The videos are truly amazing. In the description below, I'll put a link to his video that, among other things, uses a Fourier series to sketch out a portrait of Joseph Fourier. I must admit that I'm tempted to show a few more interesting trajectories, but given the length of this video, I think that's better saved for another time. I hope you're impressed. By using the magic of Fourier's series, we've been able to construct a situation involving moons upon moons that ultimately leads to the final moon having a trajectory in the shape of a square or any other shape we might want. How cool is that? Unfortunately, unlike the nearly square orbit shown in the previous video, the situation here is not physically realizable. The main problem is that it's inevitable that there will be close encounters between some of the objects, so our assumption about circular orbits just doesn't hold. But if you're anything like me, the fact that such an orbit cannot physically occur in nature doesn't dampen my spirits one bit. I mean, did you see what we actually accomplished here? We started with an arbitrary shape, which is So who cares whether or not it can be used to model an actual moon system? That's just not the point at all. Sorry about that. Sometimes I get a little carried away and hard to contain myself. But with that, I'll bring this video to a close. I'm David Jackson, and I'll see you next time on All Things Physics.